So this webinar is recorded, the slides are recorded, and it will be posted on PMC website, on my website. This is I think is 72, but some of them I repeat because I didn't have the tool to record the video at that time. So it's a collection of presentations for the power transformer life cycle improvement, and the first package of slides come from the ABB. So that's the Agerna transformer life cycle, healthy, not so healthy, repair, oil purification case studies. So that was the key agenda list for this presentation. What's the shape of the transformer, good, bad, comparing that with people and aging people, you know, the same we're gonna find in the other presentation. I have here a few of them. This is from ABB, and then the others will be like Kinetrics, will be a very good one, and Siemens specialized mostly on the paper insulation. So diagnostics, very important to know where we are with the transformer health. Challenges: aging population, increasing pressure to improve utilization of the assets longer than originally we accounted for. Let's say we had 30 years in plan, but now we passed 50 years and we still consider the same power transformer that is still having some life in it, especially if we do the reconditioning, changing most important parts that deteriorate, like bushing and gaskets, and changing the oil and so on. So we will see what kind of tests are recommended to actually acknowledge the situation of the transformer and what can be done to fix it. It happened the same in Darlington, where before the actual outage start of the unit 2, the first one going offline for the refurbishment, we had a lot of assessment on the distribution system, the 44 kV, and we found out that we don't need to replace those oil transformers on DS1, DS2, DS3, 4. We installed some extra switch gears, like switch gear 50, 51, 52, 53, that was for the new buildings, right, the RPO and stuff like that. But the old distribution systems, they were up and running, and yeah, we refurbished the transformers to prepare for the next at least 10-15 years going forward. It's not worth it to refurbish a transformer if you don't have at least 10-15 years in advance. So you cannot prolong the life for a year or so. It's not worth it. So challenge today, as we said, cost, money. Everybody's scrambling for money, and yeah, probably one day this will end. But for now, we are all trying to reconsider the existing equipment, population of the transformers, over 40 years of service. You can see that industrial transformers, they have high risk of failure. Once you got 60 years in service, 40 years in service, so the years in service are the bottom on the horizontal, and then the risk increase up to 60%. So it's kind of going hand in hand. As the transformer is aging, the increase of the chance of failure is higher. And you see these three curves. One is for industrial, the other is for power generation transformers, and the low bottom curve is for transmission, for Hydro 1. Okay, so industrial are the more exposed because they have a lot of switching and stuff. Generation is second, and the network is the third. Any questions till now? No questions? Transformers installed at critical parts of the network. So without the transformers, we don't have a network. You need just about the big picture, you need a transformer that is stepping up the voltage from the generator. Usually generators are 20 plus kilovolts, and they go up, depends what station, 500 kilovolts for Darlington and Bruce, except unit 1 and 2. Unit 1 and 2 and Pickering, they are 230 kilovolts. So we need to step up the transformer voltage on the high voltage, because the transmission line need to be on a cross section that is supported by that current, so the current as low as possible for that power. Therefore we go with the voltage up. So that's the reason. So that's the step up transformer right after the switchyard. And then we have transmission line transformers that either modify a little bit the voltage as they get closer to the city and closer to the load, less load, so they distribute the load to different sections of the transmission lines. Those are part of the transmission substations usually. And then we have the step down transformers again to the distribution, like we have the distribution 44 kV and 27 kV in Ontario. Those are the medium voltage, and further down to the building, so 600 volt and whatever the end user needs, 3-phase 208 for your house and so on. So those are the transformers that are everywhere. It's a technology that is very mature. We have this for 100 years out there, more than 100 years, so it perfected and is very robust, very well known, controlled, and we know what to test and what are the weak links and weak points and how to avoid catastrophic failure. We know all that already from the experience, as I said, of over 100 years. Now I need to tell you that the actual transformer is nothing else but an induction motor. It may surprise you, but induction motor and transformers are actually the same thing. The difference is that the mechanical movement in transformer doesn't exist. So it's only the induction that happens, but the transformer definitely doesn't move the secondary. So, but it's the same principle behind, is the induction law. Okay, so induction motors we also have for kind of the same 100 years plus around. Life cycle effects on transformers. We have here incident stress of the insulation. So as the stress increase in strength, we actually derate the insulation, and the insulation is closer to a complete failure. New transformer on the left, old transformer on the right, and that's with the increasing in age. You see on the beginning the transformer is able to sustain those kind of faults without having a final failure, but as the transformer age, that margin disappear, and for the same failure that was still supported by the transformer at the very end, when it's old, the same thing will just destroy the transformer with a final failure. Same with us. So it's very, very much analogy with people in many regards. You're going to see that on the slides. Typical trends to fail. Well, Doble, which is the manufacturer of the one of the most important for the testing, we got 43% of the failure come from the windings of the transformer, 19% from the bushing of the transformer, and then 16% from the tap changers, especially if they are load tap changers. Okay, that ends up in a 78%. Now IEEE and others, they may have slightly different percentage, but the difference is non-significant, is basically in the same ball game and the same order, so that doesn't change. So transformer life cycle, to be manufactured properly, born healthy, life healthy, so how is actually maintained during the lifetime. And then new lease on life is when you actually refurbish the transformer and you prolong the life of the transformer by doing what we said, replacing the components that are usually failing, and having the proper operation of the transformer also is very important, because you don't want to have the transformer to actually fail on the overload, or because you are keep testing the transformer more than it should. So the transformer testing and powering up the transformer does not help with the prolonged life. So the less you do energizations, the better is for the transformer. To be honest, the transformer will be very happy to sit there at 50% full load all the time, as around that value, as constant as possible, without energizing, de-energizing. So benefits of knowing and condition of your transformer: reliability, life extension. Now with the overload, you can also apply the IEEE standard for overload. We have procedures to get the transformer prepared for a known overload that is coming. That is to actually activate your forced cooling for the transformers that are oil cooled, forced air cooled. You have those 2 or 3 stage fans at the back that you can actually activate and force to cool down the transformer to the maximum possible before you apply the overload. So what that's gonna do is gonna just maintain the transformer cooler, and it's not gonna get to a point where it's gonna break down. The temperature will increase because of the overload, but if you start already hot, the overload may take you over the limit. Or if you start very cold as possible, let's say you start those forced cooling a few hours before the overload is expected, you're gonna get the transformer increasing in temperature but not reaching that critical breakdown of the insulation temperature. Assessment: site support, oil physical analyzing, transformer test results, loading, ambient, significant event. You need to keep an eye of everything that happened on that transformer, like history. First of all, you need to have a benchmark from the manufacturer when they release the transformer. Then you need to have another benchmark when the installation of the new transformer happened. So all those parameters are the starting point, and from there on you're gonna get the evolution of the transformer and keep all those data, perform trending, and that will help with anticipation and prediction of the transformer failure. And yes, we will have different methods to counteract, but at the end all transformers will have end of day, irregardless how many times we keep maintain or change oil. It will be coming to an end, but that end can be very far. So as opposed to the 30 years original predicted, as I said, we still have the 50 years transformers in the park out there, and they operate very nicely, properly, and we predict that another 20-25 years is what we can get out of them, which definitely is a huge saving as opposed to manufacture and replace them right now. Risk of failure: short circuit, winding conditions, risk of dielectric failure, assessor failure, and random failure. And here is a map of the failures. Risk of failures can come from all this. Pretty much you have here category 5 categories that are listed here, and you have the short, the thermal risk, the dielectric, breakdown, accessory risk, which include the tap changers, and then miscellaneous risk from other elements like the motor of the tap changers and so on. Any questions? No? Stress acting on power transformers, mechanical stress, that's what I said. When do we stress the transformer mechanically? Anytime we energize the transformer, we have forces between the windings that are proportional with the square current. So mechanical stress, huge at any energization. Remember, the inrush current can go up to even 21 times. In the ETAP calculation we have 12 times, but it is actually higher. Thermal stress, so that energization. Also any short. Clearly, if you have a short circuit, that will act as a mechanical stressor as well. Whenever you create high currents in the windings, that ends up in a high mechanical stress. And don't forget, these windings are in the coil of the transformer, mechanically posted and maintained in position by different methods, and those may break down, and then you have loose windings collapsing and so on. Thermal stress. Thermal is overheating, right? So we have a temperature monitoring on the transformers. We can also observe the temperature with infrared cameras. So what that does, the temperature, well, is gonna accelerate the aging of the transformer. We don't want to leave that transformer on overheat. So how do we make sure that doesn't happen? Is easy. Don't overload the transformer. Make sure that you have the oil, pure oil, and no sluggish into the tubes that can clog the radiator. Now, how do we read the temperature? Normally is an element in the middle leg that is the hottest on the 3-leg transformer, and the middle leg on the top has a temperature monitoring system. That's why it's giving you an average temperature, an alarming and even trip of the transformer. However, you do not have a reading of all the temperatures in the transformer in different locations. So for that one, you need to do scanning with the infrared camera, because you will not see all little tubes. If they clogged and they have a local hot temperature, will not be indicated by the general temperature reading that is in the middle leg top. Dielectric stress, any over voltages. So over voltage coming from discharge, like you can have natural discharge, or over voltage from switching, like Hydro 1 will switch the transformers for paralleling and giving backup transformers for the load. Those create high voltage switching capacitor banks for power factor and voltage correction. Even tap changers can give you over voltages. So anything like that may create a voltage stress in the dielectric. Okay, so those are the stressors. Leakage flux. Well, this happened also in Pickering and transformer unit 5, main output transformer. We got somehow the magnetic core inside the main tank, right? The magnetic core should have a certain definite position, but if it's moving during transportation, or is moving during a severe short circuit because of the forces, definitely this will get the magnetic core of the transformer closer to the tank, or by design, by calculation, miscalculation, so the design wasn't proper and you got field, as you can see at the top, closing to the tank top cap. So if you have that, the leakage flux will induce a voltage in the tank, and the tank is grounded, so you will have current circulating through the tank, and that will end up heating up the tank. So overheating the tank is contributing to the total heat of the transformer. The whole efficiency of the transformer goes down, because that field that heats the transformer tank does not operate as a useful magnetic field to induce voltage in secondary, so your efficiency goes down and you have higher losses overall, right? So heat generation over the normal temperature can be generated this way. So was repaired, the transformer was open. ABB transformer is a 500 MVA in Pickering B, and they corrected the core position and solidly fixed to the actual tank with insulators. One thing you should know, we also test the dielectric insulation between the magnetic core of the transformer and the tank, and that need to be in the order of minimum 10 mega ohms. So that's one of the tests that is telling you that you are too close or something happened with the dielectric with oil inside the tank. So we should have at least 10 mega ohm. Depends on the aging, it may be even higher for a new transformer, 100 meg. Okay, so that's dielectric calculations. The manufacturer will do all these calculations for bushing, equipotential. The bushings are stressed in electric field, not magnetic, like we saw the leakage inductance there, in the tank, this is electric field. The electric field is just gonna flow through the bushings this way because is actually connected to the power cables, but from there to the actual three-phase in the tank. But in the middle is passing the tank. The tank is grounded, so the actual voltage electric field is zero. So that's why you have stress on the bushing all the time. So the bushings are a weak link, as you saw. That is the third factor in the after the short circuit of windings and the winding collapse. The third was the actual bushing failure. What can be done? What can be done is a manufacturer or the designer should ask for a bushing size at 150%, and that will give you the peace of mind. The bushings will not collapse easily being oversized. So that's a known method, but you know, price is another criteria these days, and sometimes they don't like that extra. But that's technically speaking the solution. And maintain the bushing, of course. You need to clean them and maintain them clean. You cannot have debris, or the bushing can be destroyed by animals running across and being zapped by high voltage, and you know, it happened in different places like Ottawa Power Station. Insulation design outside the winding. So here is a actual 3D plot of the gradient of temperature around the connection windings. Interface transformer 3D study. So again, you have the temperature here, the gradient around the insulator, the cone that connects the cables. Life assessment, final calculation of the transformer life is how much life remains. There are IEEE guidance, winding hotspot temperature evaluation. So this is what we're going to discuss in these slides coming. Oxygen, moisture, life remaining, and recommendations. So advanced diagnostic testing. Then base diagnostics are related to the resistance of the windings, balance of the windings. We do that with actual micro-ohmmeter or ductor, another name for the same micro-ohmmeter. So we expect maximum few ohms per windings. Then we have ratio test of the transformer that also give you the health of the transformer. Oil tests with the DGA, we're gonna go more in details about those. Each test has a standard that apply the way the test should be done for the dissolved gas analysis. The major transformers, like the main output transformers, will have online monitoring. A smaller transformer like 10 MVA or 20 MVA will not. But the main transformers, the MOT and the UST SST, they do have online monitoring for the base gases, not the extra. So does not calculate or indicate all the gases, but the basic 8 of them. If you want to perform more tests because you are still not decided what is wrong with the transformer after you know, the normal call-up test, you have available additional testing that can be done for partial discharge with acoustic. So that is indicating the partial discharge going on in the transformer in the time that is powered. Basically you listen acoustically. There are different methods, but one of them is to acoustically listen to the discharge. They make a noise, and the frequency of the noise, amplitude of the noise can tell you about how much discharge you have. If you have a lot of partial discharge, more than normal, then you can actually consider the transformer is at the end, beginning of the end. We call the partial discharge in motors and generators and in transformers that are the cancer of the insulation, and it start deteriorating as a permanent deterioration. SMR is the frequency response measurements. There are characteristics that tell you the health of that phase. They need to be alike from the three phase or between the same type of transformers. this is like the power factor for different frequency. We talk about insulation power factor, which is defined by the trigonometric cosine of the reactive current flow in the charging of the insulation over the total, or you have tangent delta, which is the same thing but is taking the complementary angle, that is the other part difference to 90 degrees, and is the tangent of the reactive current charging capacitive the insulation divided by the resistive leakage current. So either or, they show the same thing. For local power factor, insulation power factor reading will be at 60 Hertz. Do not confuse this power factor with the power factor of the electric circuit. The electric circuit power factor is simply defined, as a reminder, as a cosine of the angle between the phase current and phase voltage. So that is the power factor per phase in electric circuit. Now this one, you can put similarity between the electric circuit and the magnetic circuit, because you have the ampere turns, the coil, and then you have the magnetic field as a current, and then the magnetic resistance as a load, and you can build similar circuits in the magnetic world. But just remember this, the switching frequency is for variable frequency. It's starting for very low, 0.1 Hertz, and it's going up to 100 kilohertz. So you will see the graph, frequency response, and this is for the health of the insulation windings, dielectric paper insulation that keep the winding in place. Okay, so each test has its own outcome. Spectroscopy with the actual parts, ppm per parts per million from the paper insulation that are in the oil. So that is also correlated with the Farran test. On-site testing, so limited to the on-site testing, and then you have other tests that can be done on the factory or on, it's still on site, but they need to come up with a zone they set up same as a factory, and they do the rest. Surge testing, DGA, surge is the inrush current, the magnetization current, and that need to stay the same. Materials and oil testing, particle count, as we said, oxidation, furanic analyzing, and polymerization testing for the oil, how solid, or for the insulation paper. So the oil, not only the gas is dissolved, we are interested in the actual strength of the oil as dielectric, and also we are interested in the oil capacity to cool and purity, so the color is also classified in the ASME standard. We have a standard for each test. Dissolved gas analysis. So the DGA, with this slide we go in the DGA, gas rates increase for key gas detection, history of the, you need to trend, and you need to see per each gas what is the value, how close you are to the limit. And then for some methods, like Rogers method, is actually using the ratio of different gases, not the actual value of the gas. And the other thing is the rate of change. Like anything else, we want to know the rate of change. So if that is too fast, so we have something that is getting closer faster to the limits because it starts to generate more gases, then we need to increase the number of readings. If it's not online, then on the normal reading, let's say, is once a year that we take some oil sample. If you want to perform all the gas analysis in a transformer, you will need to extract 1.41 liters from the oil in a safe manner. So there are syringes that are totally insulated and does not allow ingress neither in the sample, neither in the transformer during this. So example of problem, axial winding collapse. You see here the picture on the right, hoop buckling, excessive compressed force during a fault, and shorted threads at the bottom. So those are the typical outcomes of degradation, interpretation compared to the reference, have your own trend and library. That's very important for the system engineers. Dielectric frequency response. So here is the curve. You can see it's from 001 to 1000 hertz. Each point is actually a power factor of the insulation. You see power factor there 00324 and so on. So we have dielectric frequency response, provide information about the dielectric behavior of the insulation system property of the cellulose and oil insulation separately distinguished. Now, if we have moisture, the moisture on a temperature that is, you know, in the operation type, in the range of 80 degrees Celsius and above, we don't have moisture much into the oil. So the oil being hot, is in the oil, not in the paper, because the windings are hot. Once we cool down the transformer, that moisture will migrate from the oil inside the paper insulation. So that's why when we do samples of oil, it's very important to mention where was taken. So was taken during the operation. You can take oil from the transformer at full power, or was cooled down and later the sample was taken. So we need to know that, because it's different margin and different results. Any questions? Do you have any questions up to now? Okay. Transformer fleet. So we should have something like that, you know, about our transformers out there. Don't forget, everything that is 20 megawatt and above is part of the bulk electrical system. So we should take seriously those transformers, 20 megawatt and 20 kilovolts and above. So everything that UST, SST and MOT, those are part of the bulk electrical system. That's why we have duplicated protections on group A and B and so on. So they have special treatment. This is just an example. Risk of failure, you see red, yellow, green. We classify our system the same way. I think we said also we have white, I think, in the color of the system. So red, urgent, yellow, preventative, and green is normal operation. Repair, manufacturing. Decision, repair or new, is based on the age, design, availability, power rating, voltage, extent of transformer repairs. Future plans, risk of failure from those criteria of failures that we discussed. And then lead time for new transformers. Yes, you may want a transformer, you may have the budget, but you should consult with the potential providers what is the delivery time, because this is a long lead item. New transformer will not just come on site next day after putting a PO. It takes time to manufacture, to test, to actually have this delivered. Transportation should be done with recorder for impact. Impact recorder will record any impact, and if it's anything larger than acceptable, the transformer need to be tested again or shipped back or repair on site. Okay, so these are the factors for the decision between repair or new. Typical early and midlife refurbishment. So here are the major subcomponents of the power transformer. You see silica gel at the bottom, so that is for excessive overpressure in the tanks. There is a silica gel that absorbs the moisture, so you can release the oil safely. And then you have the on-lap tide changers, the bushings and oil level. You have the extra tanks on the left. That is the expansion tank when the transformer heats up and you want to maintain that oil available, right? But in an extra expansion tank. Against the overpressure of the oil, we have Buchholz relays. Buchholz relays, they actually measure the overpressure of the oil in the tank, and they act to disconnect the power if that goes rapidly up. So overpressure means indication of possible explosion. Those overpressure relays, they actually act faster than differential relays for explosion, if that happens in the transformer, the differential relay will be actually second in line after the relay 63 Buchholz, which is the fastest, as I said. Oil DGA, right? So we have dissolved gas analysis and temperature indicators. So what we indicate locally on the instrumentation on the power transformer will be the tap changer controller will indicate the position of the tap and so on. Then we will have the primary secondary voltage. The tap changer usually is on the low current side, whichever that is. For a step up transformer will be on the secondary, for a step down will be on the primary usually. And you have steps of plus minus 2.55 and 7.5%. The tap changer happens with contacts that are make before break, so eliminating the sparks. As a tap changer construction, we have the oil cooled and the vacuum. The vacuum is the new one, and they last 1 million operations. The oil one is half, like 500,000 switching. Online tap changers will change whenever the voltage is not right to correct the voltage on the output. Is not fast enough to correct the voltage in a dynamic matter of a motor start, is only good for static load change. Okay, so you measure you see the low tap changer position, you see the currents primary secondary, you will have some ammeters eventually on all three phases for three-phase transformer, also the voltage primary secondary, and you're gonna have a temperature reading on the mid-phase stop. So those are the instrumentations that you see, plus the force cooling fans with the controller and the sensor of the temperature that start automatically based on the tank temperature. Okay, any questions? No questions? Transformer repair. Here are the replacements we talked about: tap changers, cleaning, drying, new oil, repair of the tank, shields, retrofit, modernization, gaskets. Everything that's gasket, we know they crack. Make sure the gaskets you put are not at the end of the life life, because if you keep a gasket in the storage for too long, that is actually unusable. So anything that is not crystalline, metallic, and does not have a shape, that is not flowing, plastic, rubber, and stuff like that, does not last too long. They have a life, shelf life, and they need to be maintained in a certain place with temperature, humidity, and so on, so you can use them when they need it. Also, over torquing can crack, gaskets. So this is a two-way street. So you want to improve, but it's possible to actually make it worse with replacements. Repair in the factory, examples for different rating of the transformers. Well, we repaired in Pickering. We had a severe dead short on unit 7 back in 2006, I think, was a thing that went a little bit sideways. The power was energizing the main output transformer with a dead short, because the actual safety grounding leads were not removed. Were declared removed, but they were not. So the whole transformer 500 MVA three-phase moved few feet, elongating the bus bars, and yeah, that was a very dangerous stuff that happened. And then repairs on site, like 3 months with ABB, setting up a tent around the transformer and doing all the repairs, all the testing on site to avoid transportation, because for transportation you may need to empty the transformer of oil before you send that off, and then when it's coming back empty, you need to refill. The refill should happen as you don't insert any moisture in the transformer, right? So it's a pressurized system, sealed system. No moisture should go in or out. Now in the transformer, yeah, you have the silica gel, some of the construction for overpressure to release extra oil on the pressure. Also, you have 3 compartments. You have the main compartment of the oil tank, then you have the low tap changer that is in a oil, and they communicate via valve, so you can put oil back and forth, and then you have oil on the bushing compartment. Sometimes the bushings are cooled down with nitrogen for high power. So it's a blanket of nitrogen on top of the oil that actually cool down better the bushing. Better insulation and better cooling. Here is an example of the ASEA Brown Boveri transformer transportation. Contamination, anything that is FME cannot go in the tank. We had that also, people drilling in the tank to hook up different wires for fire protection, alarms, and they didn't realize that the edge of the tank is actually part of the tank and the oil spilled out. It happened in Darlington back in 2019. We had some silicon field 20 megawatt, and they tried to post the actual fire protection alarming wires, repositioning them, and they considered that is okay to drill in the edge of the tank, but was not. So the oil came out, which means you could have these sharp filings in the transformer. Very dangerous. They collect electric field and they can get out to 10 kilovolts on the edge, penetrating even NOMAX and going through. It happened not on transformer but on the UPS class 2. We had this event, and since then we have the FME procedure, foreign material intrusion. So you need to cover with blankets when you drill and use magnets to clean up anything that is around, and use the vacuum cleaner. And there is a full procedure to avoid this kind of stuff. Take it very seriously. Any filing like this inside the electric system is a big danger, huge danger. Tank damage from explosion. Well, explosion come with products, chemical products that need to be cleaned up, is very costly. Plus the explosion is something that is permanent damage to the equipment, but is dangerous to the workers and public. So fire can get on fire, and then you got high temperature developed, hundreds, few hundred, 400, 500, even 700 Celsius. Tank damage, active part with collapse of the windings. You see here repair of the same core. So if the core is okay and you don't have short circuit between different lamecoidal core sheets, those are 0.35 millimeter to decrease the actual losses, eddy currents and hysteresis. So you should have insulation in place between them. They also deteriorate from movements and active short circuit or too many connection of the power. Repair active part, low voltage side, and tank repair. So this is a success story when the back to site after the damage that you saw happened. Repair examples, here are more of that, more on-site and off-site repairs. Key to the success on the site repairs, creating like a factory environment around, free area, and all the procedures apply same as in the factory with no dirt or ingress, and testing at the end of the repair is mandatory. Same test that you do for new transformer. Active part handling, you see, operations. Certified site supervisors need to review and supervise this kind of operations from ABB. Nobody in Bruce or OPG or any plant is qualified for this work on site. They will come from the ABB or from the other manufacturer that is the manufacturer of the transformer. So they are specially qualified to overview and supervise the process of repair on site. Drying the active part, we apply drying a lot of times. We have moisture, we apply drying by low frequency. This is a process that is applied for the motors that were not properly maintained on site and they got ingress. We applied the heaters, anything like switch gears and even generators, they need to have a certain minimum percentage or maximum percentage of moisture. If it's more, they don't pass, like motors or transformers, they don't pass the Baker test. they have a very low polarization index number, which means a lot of moisture in the windings in the actual insulation, and that is not acceptable. So to put it in service, you need to pass all those Baker tests, dielectric test, PI test, tangent delta, and so on. Active part drying. So here is an example of drying out with low frequency heating. Drying with low frequency block diagram. The converter that provide that power to the transformer, and then the vacuum pumps. Taking also moisture out. Oil treatment plant in the same time. You recirculate the current, and yes, the transformer is offline because you will have to actually supply this low frequency from the converter, not the real power. But the reconditioning of the oil can happen during the normal operation. Actually, we will see the slides. So transformer testing on site. Here are measurements, turn ratio as we did, winding insulation short, impedance, dissipation factor with double or Megger. Those are the two main companies. Frequency response, dielectric frequency response, partial discharge, voltage test, 500 kilovolts. So measuring can happen at a voltage that is less than the rating. High pot test is only happening at higher voltage, like 1.5, 2 times the voltage, depends on the age of the transformer. And load losses, reduction, lightning impulse, and switching impulse. So those are the tests that you do on site. Oil purification, problem, oxidation of the oil, cellulose, solution, reclamation. Reclamation is a process that can be done on site and is done over a day or two with a special equipment that connect the transformer to the reclamation truck that filter out and take the gases out and particles, so it confer a good reconditioning of the oil. That's why it's needed, so we explained that. Benefit, yes, very benefic. But if you consider that reclamation is not a solution, you can go for a full oil change. For all the transformers, you will do the oil change slower because the paper insulation may actually be contaminated with moisture, and because it's soft, it may break if you release the oil at maximum open valve. So you have smaller valves and you release the oil in a slow pace. Oil reclamation definition: either you take the IEEE 57106 or the International 6422. Reconditioning of the oil, right? So here are a number of things that need to happen with filtration and dehumidification, degasification. Those are the requirements of the standard to consider that reconditioning was done properly. Okay? Here is the actual block diagram for the reclamation. You have the truck with the all the filters and everything, that absorbent, columns, degasser, and return to the conservator is the top tank on the transformer. Oil reclamation, acid, sluggish. Those sluggish that are developed in the oil are actually acidic. They corrode, they clog the tubes, and also they are very good electrical conductors, so they form a partial discharge and arcing inside the oil. So you want to get rid of that. The oil should be as clear as possible after this, close to a light yellow, not dark black. You can add antioxidants and other nitrogen compounds to slow down corrosion. Okay, so insufficient treatment time. So when the reclamation goes right, because it wasn't done properly in the time that you need to allow 24-48 hours, it may happen that actually the sulfur convert in more corrosive forms. because of the incomplete reclamation. So those are the coil, like 4, but they are actually 8. In between there are other 4 oil colors, and as I mentioned, the lighter, the more clear, transparent, whiter is the better. And as it's getting darker and more burned out, the oil may be even at the age that cannot be reconditioned and you need to replace. Recall the transformer life cycle. So we saw this slide, we just repeat how it's born, how it's maintained, and how it's extending the life. Different cases for repair and manufacturing, for degassing over 20 years transformers, solutions with low frequency heating, tank repairs, examples 400 MVA transformers, hydroelectric utility overload studies for the transformer here, temperature increase, industrial customer design. Rectifier transformers are a special breed, same as the UPS transformers, everything that come in contact with the power electronics, switching large power. You have a lot of THDs, total harmonic distortion, especially from thyristors. So when that happens, you need to actually design the transformer for insulation that keep up with those harmonics, install filters, zigzag transformers, and everything that clean up the system from those harmonics. Or if not, at least you have the the transformer few turns of the insulation increasing in thickness, low capacity cable that connect, and so on. So there are techniques to have lower dissipation of the heat and stress from the THD, total harmonic distortion, including the shape of the copper. Not necessarily will be the conductor that we know. It may very well be a rectangular or even a shape of a plate going around the leg of the magnetic core. Now also magnetic core, as you know, there can be one phase, 3 phase, but also the 3 phase can be as a manta transformer that has 5 legs. The last 2 on the side are half cross section, and they there only for the uniformization of the magnetic field. Because on the 3 leg, the mid leg always has more stress, even the magnetic field is higher. Rectifier transformer, hotspots, and so on. So material are special and the construction is special. Also what we need to take in consideration to clean up the harmonics. Because converters, they always create harmonics. The harmonics in the systems are either created by switching power or by non-linear elements like magnetic core saturation. Those create third harmonic. Okay, ranking of the in-service spare transformers based on all these criteria. You can see here maintenance, short circuit, winding thermal, general, power factor, acetylene, hot gases, carbon monoxide, hydrogen, and time in service. So those are the bullets that you put on top of each other, and then you see, for instance, unit 1, 2, 3, 4, where do you want to be, where you are with the life, because of this criteria that you apply. And then you have a spare transformer that is like new and has all those margin still available, but you burned a lot of that out already on the existing 4 units, right? So you have much less available. Hydroelectric facility, fleet study across the fleet. That's come from Hydro 1 and GSU, that is the actual unit transformer, hydro station. Example, leaking 750 MVA transformer, 500 kilovolts. We have leakage points in the tank. You see ASEA Bromboveri transformer. It's called also Hitachi. Don't be confused. Everything that you see Hitachi, or 90% of what you see Hitachi transformers, breakers, and so on, is actually ABB. Well, this is what it is. It's called ABB in the background, but is having on top of a name, you know, Hitachi. So oil leaks, you can see here coming out of the tank. Keep in mind, whenever the oil comes out, the air goes in the same spot. Not only get you lower oil and cooling, but you got moisture getting inside in the same time. Simulations, on-site repairs. There are different software to simulate the forces, the distribution of the temperature and cooling of the transformer inside. Here is the same transformer with the repair done on site. Coolers, 20 years, need to be replaced, typically because of the debris and trapped sluggish, blocked oil flow. You can see the over temperature in a certain place and so on. And this is a failure for a transformer, complete failure, and so on. So this was the ABB presentation, and I think we kind of ended up with the time 1 hour. There are some other things that you can see on the same PMC folder. I will put this ones. Is the same idea, comparing transformer with people, and more details about the syringe and how you take the oil out, and some procedure used to evaluate the oil quality more in depth in the kinetics. And then we have the Siemens. That Siemens presentation is very detailed into the paper insulation, chemicals and composition, and breakdown the cellulose paper. So you have some more details in the Siemens presentation here that we will not go through, but I tell you what will be on the webinar folder on the PMC side. The link is on the invite. And then there are 3 general presentations that I don't intend to go through, as a theory part 1, theory part 2, construction, and then theory part 3, construction and operation. So there are 3 package of slides for the theoretical part, and then we went through the ABB from my friend Todd here, and then we have kinetics that is highly recommend to go through, especially for the oil. Has more details about the Duval triangle and how you evaluate this DGA, and Siemens that is very strong into the evaluation of the insulated cellulose winding insulation. Now OPG and Bruce, they send these results after taking the sample, 141 liter if they want the complete test. They send including the acidity test and the dielectric strength and all that, quality, the ratio of the two. They send it to Kinetrics, because Kinetrics is still having the database for existing transformers. They were one time part of the Ontario Hydro, one of the big 5 companies, right? So Bruce, OPG, and Kinetrics, ESA inspectors, and NSS for the actual nuclear part. So they were all part of one, and Hydro one for the transmission as well. They one company. So we have those transformers data. Sometimes for outside the nuclear fans, we send it to Montreal. It's another company that does that online, and you can see practically the results next day. Okay, so that will be my presentation for the actual evaluation of the power transformers, and we didn't mention some of the specific tests. I had another webinar in the past for the collar test, just to test the bushing. So yes, this can be much larger presentation, but I keep it to 1 hour. So we have 1 o'clock, and I ask the audience, if you have any questions, please do not hesitate to ask or send emails, and let me know if you want any other topic that's specific for what you are interested in. If not, if no question, thank you very much for attending, and I hope to see you to the next webinar, probably in a week. And if you have a topic that you are interested in, send that email and I will accommodate. Thank you again. Have a nice day and a nice, safe, long weekend coming up, Canada Day. Thank you.
Thank you.
Thank you.